Mark, and thanks everybody for being here today. We're really excited to have Gary Klein back for part 2 of Passive House Plumbing. And as you have just heard, part 1 was very exciting. So we're anticipating some thrills today during the presentation. So a little bit about the Passive House Accelerator. We're a collaborative online platform for sharing innovation and thought leadership in passive house design and construction. We publish articles and interviews, produce weekly virtual confabs with passive house pioneers from around the world, and we elevate the work and programming of the passive house movement's leaders, practitioners, and organizations through interviews, articles, social media campaigns, video, and podcasts. Our aim is to catalyze zero carbon building by accelerating the adoption of passive house building. With our co-hosts, Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce Construction Tech Tuesday to share the technical, the technique, and the technology of passive house construction. Each week, we welcome guest practitioners to dive into the details of practice with the builder and tradesperson as our target audience. We welcome folks from all corners of the construction and design world to join us each week, and we're really happy to have you here today. So we're going to now throw it to Dylan Ingwe, who is going to tell us a little bit about a community, online community, initiative, I think is a better word, through Discord. So with that, Dylan, can you take it away?
At Passive House Accelerator, we are going to be launching a Discord server. So for those who don't know what Discord is, it's basically just like your stereotypical like Slack or chat room, Facebook group, whatever you want, Microsoft Teams. It's very similar. It has a bunch of different chat rooms, a bunch of different things you can do. So quickly, just to kind of like show you guys kind of how to join and how to deal with that process. So first, what you're going to want to do is you're going to want to go to discord.com and kind of make your account real quick. Just because it'll be way easier later if you just do that first. And then you're going to click on the link that I'll post in chat shortly, along with a bunch of other information. And that should work, hopefully. So once you get into the server, you're probably going to be thrown straight to this rules channel. So please do read the rules, just because it's nice that we're all on the same page. We all know like expectations, etc., because we all want to have a good time. So it just makes sense. Just read the rules. They're pretty easy, pretty, just be respectful, be nice to one another, etc. But after that, I'm going to ask everyone to go to the rules channel. So it's circled right there in like big red. So it's like a few under rules. So you're going to click on that. And this is the most important channel of the server, just because it introduces a really cool feature that I think once everyone gets on is going to be used all the time. So, the thing that we all do in Zoom chats where like, let's say I want to talk to Zach and I want Zach to read my message. So I'll go at Zach, look at my question, please read this. On Zoom, as we all know, it doesn't actually ping Zach, but what's cool is on Discord, it does. So if I wanted to ping Zach, I could do at Zach and it will send a notification to his phone and to his computer saying, oh, you got a notification, check this. And that's really cool. And then you can also do that for all the different roles we have here, as you can see. And so that just makes it really easy to ask questions, really easy to interact with one another. And then this is just kind of introducing the channels idea. So all of these on the left side, so that's like rules, roles, which we just went over, and now general. These are all what we call channels. So you can just kind of click to change channels, and all of them kind of have a different theme. They all kind of make sense. General is just for like general conversation, Q&As for questions and answers. Ideals is if you want to share an idea with everyone, etc. They're all pretty, common sense. And if they're not, you can always DM me and ask me, hey, what's this? And then also nicknames. So you're probably going to make like a really weird, username because you don't want your username given to Discord or to any random, application that you just downloaded because some 17-year-old child told you to. So what you're going to do is you're going to click right there where the first arrow goes up here, right next to where it says Passive House Accelerator, and then you're going to hit change nickname. So the reason why we're going to do this is because here, it kind of lets you put your real name so that we know who you are and everyone else knows who you are. And that just makes it really easy to, communicate, etc. And so we're going to kind of try to follow like the first name, last name, pronouns in parentheses kind of format. So like, for example, for me, that would be Dylan Ingui, he/him. And then also you're going to want to eventually update your profile, just because as you can see, the highest message in this general channel, I don't know if you can see me kind of like going over that, but that Discord icon right there, you can make that like a profile picture of your choosing. You can kind of just make whatever you want. As you can see, that's my profile picture. And the way you do that is you go to your settings and then you go to user profile, and you can hit this change avatar button, and that lets you kind of choose your profile picture. And then if you need some more help, or if you kind of want to review some of the content that I just quickly covered, you can go to this tutorials channel right here, which has a video literally covering everything I just explained, but in more depth and way slower. Or you can just DM me. My name is Dylan Ingui. It's the same on Discord. So you can just left click me and then type whatever you want to ask, and I will probably respond. So that is my quick, hopefully 2-minute intro on Discord. And if you have any questions, just let me know. But yeah, that's all for me. I'm going to put the link in the chat along with some other information.
Thank you, Dylan. And Dylan's personal phone number is 555-1212. If you want to call him and ask him what DM means. That Discord is awesome. And we get the entire month of August to perfect it. And when we do, we get a free pass to Construction Tech in September.
Nicely done, Dylan. Nicely done. I put in the chat, the only thing as cool as you is your avatar. I love your avatar. And I also like your rules. I think they're perfect, spot on. Treat people the way you want to be treated, even online. Thank you so much for sharing that with us.
So are we jumping back to Zach, or is it back to the three of us to go? Okay. Sean, take it away.
Well, of course, there's a cutter behind me, but I wanted to say, so I'm Sean Sandamore, and I keep preaching about what you see on the Passivhaus Accelerator page, where you have the Passivhaus principles, low embodied carbon, electrification, and then you add on the solar panels. So see the solar panels behind me? This is a net zero house that did that same method, where they got the right panels, the right wall system, try to reduce electrification, because again, this client still wanted their gas cooktop, but at least they've got solar panels, did the right way. So this is a net zero house. And again, this is a smoky day here in the Okanagan. So I'm going to go back inside and have a cider, a local cider, and not deal with the secondhand smoke. So welcome. Look forward to learning more about mechanicals from Gary, and follow the process towards net zero using the Passivhaus principles. Thanks for joining us, everyone.
Well, it's a shame it's so smoky there today, Sean. Yeah, it looks twice as smoky there today as it was yesterday. We saw the mountains and the valleys and the houses beyond, and it's an absolutely stunning sight. And the only thing cooler than the views is the house itself. It's spectacular. Thank you for sharing it with us. So tonight, speaking of sharing, we have Gary Klein. I'm Shannon Pendleton from Sanderson Sustainable Design, and I'm ready to get started. So open your chat. Remember to ask your questions, starting with a Q, please. And Mark, take it away.
Thank you, Sean. Thank you, Shannon. Thank you, Zach. And huge thanks to Dylan. This is remarkable. I do look forward to diving in. We're here for something tonight. We all have something in common, and that is we have water. We have water in our buildings. Almost all buildings we go to has water. And in almost all buildings we go to, it is misproperly designed, installed, and certainly used. So we can do better. We could learn from others that have made the examples for us. And I pass the mic to Gary Klein, and that's why we're all here.
Thank you very much. Well, I would like to find out how many architects are on today's call. You could just raise your hands virtually and someone could tell me how many there are. Because today's conversation is really to the architects among us. We need your help to have better buildings. Everybody okay with this basic idea? We need architects to give us better designs so we can have better infrastructure.
Gary, over half the audience is architects.
Well, it'll be great. Let's see what happens. All right, so that's the basics for today. I want to talk about how buildings are designed so that the plumbing can be connected. All right, do you know anyone who wants to reduce first cost of construction by $1,000 to $2,000 per building and about a week's worth of work? Improve customer satisfaction, right-size systems based on modern materials, flow rates, and design principles. Wondered why the well-designed plumbing system in your last building didn't work as expected? Me too. And then has anyone actually measured the performance of a plumbing system and then compared what they measured to a real design? This is one of my pet peeves, as many of you know, why pipe sizes haven't gotten smaller, even though flow rates have been dropping for forever. And if anyone would like to increase their profits by $1,000 to $2,000 per building. So if any of these answers are yes, you're in the right room. Part of today's session is based on a research project we did for the California Energy Commission. The project team was myself, Jim Lutz, Yanda Zhang, and John Keller. Our project manager from the Energy Commission was Amir AI, and we still don't have a final report published. The last year has been nerve-wracking for all the people working on these sorts of things at the commission, so we'll get it soon. I'm speaking, not the Energy Commission. We had certain goals in our agreement to develop code change recommendations that would significantly increase hot water distribution system efficiency. And we wanted to characterize the impact of low flow fixtures on distribution performance and determine the theoretical lowest possible flow for hot water fixtures. Some of that stuff we weren't actually able to do, but we have some ideas related to low flows. All right, why is it important? Well, some of you heard me talk about this in the past. Basically, everything's been reduced since the plumbing codes went into effect in the 40s and 50s. The rules haven't been revisited for pipe sizing since the 40s. Houses have gotten bigger. It takes longer to get hot water and more water runs down the drain while we wait. Okay. This is a chart showing you the analysis of consumption data from 1980 to 2017, let alone what happened before that, right? 50 to 96% reductions in flow rates or flush volumes or volumes consumed in washing machines, et cetera, certainly in my lifetime. Right? So do you think we might want to revisit pipe sizing rules? I think so. So when people talk about hot water use, this research project was done on hot water. I'm mostly going to focus on hot water today, but remember that cold water piping follows along pretty much right next to the hot water piping because most fixtures have hot and cold, right? So you sort of have to follow the same path. Most of us talk about this sort of double bump sine wave, if you will. It's not a particularly pretty sine wave, but you can see you can see the spike in the morning and then a double bump in the afternoon when people come home from work and school. This is a pretty typical perceived pattern. Weekends are different than weekdays, but nonetheless, it's about like that. But this is what actually happens. There are discrete uses separated in time and space. It is not a sine wave. There are gaps in use, and there's very, very little overlap. This is what's really happening in buildings. So we have different types of draws that we had to analyze for our research project. They're built into the modeling assumptions in the California Building Energy, the CBEC RES programs. And we use these assumptions for our basic modeling so that we could match our work to the Energy Commission's work. So here's a whole bunch of daily draw patterns in the CBEC RES data file. And some of them are really interesting to me. This is a case where there were 6 people in the dwelling for a 3-bedroom home. For number of people per household varies over the course of the year. And so the program evaluates for that. And there's only 5 such days over the course of the year. But look at these numbers. There's 200 draws and 270 gallons of use that day, those days. How does that happen? Both kids had the football teams over for a visit. And they all took showers and washed their hands a lot. I have no idea how you get this big. Okay. Now, down in here, you've got these other numbers, right? And so what we did is we looked for stuff in that rectangular box. And we ended up picking this day for our analysis. Yes, that's the day. So 52 gallons a day and about 70, 75 uses. That's sort of, and it's a big number of events. That's what we had to do to pick an analysis day. We couldn't analyze all days. So what we picked was the yellow line here, and it's 77 events, 2 showers, 70 faucet draws, and 5 clothes washer draws. That's not 5 clothes washer runs. The event happens 5 times for a cycle. That's what happens in the way it gets counted. So look at the number of faucet draws there are. Any of you ever recall going to a sink and rinsing something? Sure, your hands, your fingertips, a piece of fruit, a cup, a spoon, right? And you turn on the water. This is a classic move. You lift the faucet straight up. It's a single handle lever for most of us. You lift it up about halfway in the middle. So it's half hot, half cold, half flow. And then you turn it off. A whole event lasted less than 5 seconds. That's what the bulk of these draws are all about. That's what's going on in our buildings. All good. Let's move on. So now we analyzed these flow rates and looked at the patterns of use. 35% of the events are less than a half a gallon per minute. 51% are less than 0.8 gallons per minute, and 72% are less than 1 gallon a minute. So why are we designing our plumbing for 20 gallon a minute flow rates? I don't know either, right? Well, because we've always done it that way is the usual answer. And then we analyze the same basic set to see what the volume is. And all of the volume, 37% of the volume, is in 4% of the uses. These are showers. That's where the numbers are, okay? And there's a lot of little events. All right, so we had to decide how we were going to analyze things for this research project. We picked a bunch of different layout methods. We decided we could change the water heater location. We could have a distributed water heater location, wet rooms, or compact locations in plumbing terms. We could use small pipes, and we could change flow rates. And we analyzed all of these things in our research project. This is an example of what a diagram of what each of the different layout methods look like. This is single trunk and branch. This is 2 trunk and branch. This one over here is home run manifold. This is a recirc loop, and this is 2 water heaters. And we use this to help guide our thinking is what we're doing. We also looked at flow rates, and we had to make a name change here, but basically we're saying that low flow is federal law. And I think we should just stop calling it low flow, because kids who are being born today don't know any other numbers. So that should be just normal, right? These are the legal flow rates. And then high efficiency is when you try and do better than that. And this is what's going on in Cal Green or in Title 20 in California. Some other states and countries have adopted similar numbers. So now let's look at what we tried to do to figure out compactness. I got a couple of student interns to go look at where homes that were built in these size categories. This is single family dwellings. This was 2017. And the Census Bureau gives these numbers for the Western states, give them for any part of the country if you want, the whole country. And these are what the numbers look like. Everybody good? That's the basics, right? We did the same thing for multifamily units. And basically I gave an assignment that says, go look around the state for whatever is available and being sold in these size categories, but don't pick everything from the same town. I don't care where you find them from, but they can't all be from Sacramento. You got to go all over the state and pull out stuff. And you can do it on the web. You don't have to go drive around and pick up floor plans. You can look, let the fingers do the walking. And so we created this idea of a wet room rectangle, which is the rectilineal area that bounds the locations of the wet rooms, in particular where the plumbing comes out of the wall in the wet rooms. And then we did a similar idea for the hot water system, which now includes the water heater. Okay? And so we're doing a bounding exercise to get a sense of what's related to whom. And then because we only have these rectangles and postage stamps to look at, right, for the size of the floor plan, but we know the floor plan's 2,000 square feet, we analyze what's inside the boundary and outside the boundary in the home, and we do a mathematical analysis that gets you this answer. So we superimpose the red line and the blue line. There's some stuff over here that you can see that's outside the rectangle, but inside the envelope. There's some stuff here that's outside the envelope, but inside the rectangle. We do the proper additions and subtractions. You get area divided by total area gives you square footage of home, and magically you've got an answer. Okay. And that tells us that this 3-bedroom, 2-bath home at 1,700 square feet has approximately 67% of the floor area devoted to the hot water system. That's what we did and how we basically did it. Okay. So there's a logical relationship between the logical worst case rectilineal distance and the floor area of the dwelling. The logical worst case puts the water heater in the one corner and the last fixture furthest diagonally opposite corner. Okay. If you have 2 stories, it includes elevation, right? And that's the logical worst case. Hold on to your hats. So I'm going to go through a whole bunch of images now, not spending very much time. You're going to get the presentation later. You can read all about it later on and study them. This is the base case. This was the best we found in California that year when we looked. 81%. 105%. We got worse than the logical worst case. How about 110%? How about 155%? This one is spectacular. They have the water heaters over here. They have 2 water heaters. It's a big house. They needed 2 water heaters because of tankless gas. And so they needed it for capacity of that tub, which is going to get used approximately once a year. And then the reason they have such a big area, look, they have a courtyard. The water heaters are on the far side of the garage, and the guest suite is separated by the courtyard from the whole thing. And so you end up with an awful lot of the bounded area outside the envelope. This is what happens. Okay. Now we did a project looking at some stuff in Colorado, in Fort Collins in this particular case, and they, did better. This is only 55% of the floor area, and this is 72% of the area. So both of them are better than the best I found in California. Huh? Who knew? Now, 2-story floor plans doing the same thing. The logical worst case, if you remember, is 50%. This is showing you 37%, 51%. We broke the barrier. 58%, 63%, 72%. Okay. And then I want to point out one thing here. Notice that the bounding area is outside the envelope. The envelope's back here. Right? Why? Because somebody put a bathtub all the way out over the garage in bedroom next to bedroom 4. Why not over here? I don't know. I truly don't understand a whole bunch of what gets done. But anyway, it's what happens. Maybe the architects among us can answer that question later on. All right, so this is 72%. Notice that there's a central courtyard, which I really like. The problem is everything got spread out. Okay, this is what happens. And we're back to Colorado, 40%, and we have one at 60%. So on the 2-story buildings, they do both better and worse than the logical worst case in Colorado. As best I can tell, by the way, that most production builders build the same home everywhere. They just change the face. All right, so now we're on multifamily. This one's pretty good. It's 29%. The bounded area is pretty close. That's a pretty compact plan. It's only 1 bathroom, 1 laundry room, and a kitchen, but still, it's 29%. 33%, 50%. That's one of the better ones, right? This is 90% and 99% and 115%. So you can make apartment buildings just as bad proportionally as single family detached. Go for it, folks. Okay. Now, how do you fix some of this? Well, what if you were able to locate water heaters closer to fixtures? This is one of the houses that we've got with a water heater in the garage. If you split it into 2 zones of plumbing and think of it as 2 separate zones, you cut the bounded area by half, 30% reduction. Okay. You still have to get to the kitchen sink, right? You've still got to figure out how you're going to get hot water over there. Now we have this house, it's 105%, right? It's a baddie. But what if we split it into 2 zones? A water heater for the master suite side and a water heater for the kitchen side, which was already there, right? We got rid of all that bounded area that's outside the wet room locations. It's an idea of how to think about it. Oh, you're going to tell me how to buy 2 water heaters. Remember the house that had 2 water heaters located right over next to the garage? Okay, why are we complaining, right? It's for that tub, by the way. The second water heater is entirely for that tub. in the plumbing rules. Okay, so let's move on. How about this house? This one's, you know, a little pretty bad. It's got one water heater location in the garage. What if we split it and put a water heater just for the kitchen? That island sink in the kitchen is really hard to get plumbing to. It's way, way longer pipe than you think. It's over 25 extra feet of pipe to get there, right? Plus I had to start from here, right? I had to come from the water heater. So somewhere about this point begins my branch. That's almost a 50-foot run to that sink. And it's like, and it's underground. So did you insulate it? I don't know. I don't know, right? So if we were able to do this today, I'd probably put the water heater under the counter here in the kitchen island, and I'd make it electrical. Because of the time and year we did the project for the Energy Commission, electric water heating was not an acceptable option. So we had to pick gas water heating, and that could not go under that sink. So it had to be on the outside wall. All right. But what if we were to take this house and split it into 3 bounded areas? Water heater, I keep it in the same place. In fact, I would move it to this wall rather than that wall, right? And actually, you know, make it a much tighter floor plan. The problem is that way that laundry room's laid out. One for the kitchen and then one for the master bedroom wing, this wing here. And I get the bounded area of the wet rooms down by cutting out the long pipe connecting A to B that goes through space that has nothing to do with water. All right. So I want to share with you the plot of the relationship between the hot water system and the floor area. It's a scatter plot diagram just to show you what the relationship looks like. There it is. There isn't one. People keep telling me there's got to be a relationship, and I'm telling you the floor plans do not do that. Now, how do we fix this stuff? What do we do? So we looked at a bunch of designs, and we're trying to figure out how to match this to the Energy Commission mathematics. And that's the prototype house. Notice there's no floor plan. The energy modeling does not assume that you actually have rooms in the house. It just assumes you have an envelope and walls and floors, ceilings and floors. That's it. And windows. It has windows. But none of the windows on the floor plan are actually related to what you'd put in a bathroom. Like they're all the same size and 4 by 6. I'm sorry, that's not in my bathroom. I'm not going to let it be in my bathroom. It ain't happening in my bathroom because that's just not pretty. All right. So anyway, that's what's going on. So we had to design a floor plan for the house. It's a 2,100 square foot house. How many bathrooms does it have? How many bedrooms does it have? Remember, the commission's model doesn't say what it is. We had to pick what it is. So for 2,100 square feet, we decided to put in the wet rooms like this. And we have 45% of the area is related to the wet rooms. 76% is related to the hot water system. You can see the water heater here over in the corner of the garage. That would be a pretty typical location for it. And we put a bathroom for 2 bedrooms on either side, Jack and Jill bathroom, basically. We have a half bath for the guests. We have a laundry room in the middle. We have a kitchen in the middle over here, and the master suite is over here. And we designed it so that, in fact, you could build this house and people might live in it, okay? We tried. Again, we didn't have an architect per se on our team. We had to shoehorn things in. We could have made this design much worse. We could have taken that kitchen and put it over here on the front of the house, and I would have had over 100% of the floor area is bounded by the hot water system. So our analysis is conservative because we didn't do that. We're analyzing a better than possible case. Okay. So the reference case, we talked to one of the largest plumbers in California was on our advisory team, and we asked him what would be a typical plumbing plan for a house like this. And he said it would be a trunk and 3 branches. Water heater trunk, a branch for that bathroom, a branch for this part of the house, and a branch for the master. Okay, that's the basic idea. The trunk doesn't have to be where it is. We discussed that at great length. He said you should run it down the spine and have shorter branches, but some people run it over here. Yes, they do. It's bad design. So again, we're not picking the worst case. We're picking a probable case that plumber would build for this floor plan. Then we also looked at a compact plumbing core where we got the wet room rectangle and the hot water system rectangle down to under 16% of the floor area of the dwelling. We basically kept all of the wet rooms the same size for the bathrooms. We made the laundry room bigger because I wanted it to become my mechanical room, and the water heater is now here, right? And if I were to do this house with a full mechanical core, I'd put my indoor air handling equipment and my air-to-air heat exchanger, EVR, ERV, whatever it is, on the other side of the laundry room. And I'd be able to access all of my filters from standing on the ground as opposed to a ladder. The idea was to create a compact core for mechanical, okay? And we analyzed for the distance, and we've got the mathematics for that too. All right, so now what did we do? These are diagrams showing you this, the way it looks without showing you all the detail of each measurement. And we analyzed all of these cases. And this is the base case that we analyzed. Then we put mini manifolds, and we tried home run manifolds, and we tried one zone plumbing with an optional recirc. We never analyzed the recirc case. And we showed you where you could move the water heater, you could change different types, you could do a whole bunch of things. All of these had been built in California and around the country. We analyzed them, okay? And then we tried this idea. What if you put the water heater in the middle, like in the kitchen or in the master, right? What would it do to the plumbing? And it, you know, we analyzed for that. And we also tried 2 water heaters because people are doing all of these things. And then we also did the similar exercise for compact, but we didn't have to analyze as many cases because there aren't as many stupid ways to do it. So we just cut the number down. All right, so here's the analysis. This is the energy efficiency. And there's all the math is here. This is how much energy left the water heater, how much got used at the fixture, how much got wasted on the way to the fixture, how much was lost during use, how much was stored after in the pipe and the insulation, and how efficient was the event. Okay, and so the master shower looks pretty efficient, but the sink doesn't look so good. Okay, and here is the average for the whole house for the whole day. And this is just showing you 1 day of performance. We did this for a whole year. That's how we did the mathematics. Let's look at water. Shower looked pretty efficient, 98%. Bathroom 3 sink is pretty good, 100%. How come? Well, it's 100% efficient in the use of water. That doesn't say anything about how efficient it was in energy terms. That sink was only 56% in efficiency, 28% in efficiency. Why? The hot water never got to the sink, but the water got used. Remember all those tiny events? Water got used, not energy, got lost. Then we looked at time efficiency. How long does it take for the event to happen and how efficient is the event? The efficiency of the events with time wasn't too bad. There's some bad cases. But here's the kicker, is the service. When you turn on a tap asking for hot water, is it your expectation you're going to get hot water? Fine, I turned on hot, I want hot. Well, what if the event's over before the hot water got there? Did you get provided the service or no? No. And so when we looked at this, and 21%, on average, 21% of the attempts to get hot water, the load wasn't met. And that means virtually all of the sinks. So you're going to give up on 80% of I'm sorry, it doesn't make sense to me. We want to have similar levels of service no matter what we analyze. And I'm going to tell you that these methods are not the same level of service. Why? The source of hot water depends on which event is in which order and how far that event is from the trunk line. They're not the same. If we're going to analyze and compare things, we have to have the same level of service. Otherwise, we have fruit salad. I want apples to apples comparisons. I don't want fruit salad. I like fruit salad, but not for this analysis. Okay? So this is the best systems we evaluated. This is the energy and water savings of the best systems, and it was done under a gas year. So this is all about gas, but the BTUs are BTUs. We can do the math. And you can see we were able to save with normal flow rates, I don't know, somewhere between 10 and 16%, right? For low flow rates, you save more for all of these cases, up to 30%, a couple of cases. But most of the savings in low flow is because you're using less water, and so you're heating less water, not that you're wasting less while waiting. There's a difference, okay? And I'm interested in getting rid of the wastes in the system, the ones that we're building in, right? The structural wastes. That's a large part of my work and has been for many, many years. I'm not trying to tell you how long to take a shower or who to shower with. That's not the point of this exercise. The point of this exercise is to get rid of the unintended waste that you didn't want in the first place. Do you know that the average US shower is 8 minutes long, has been for almost 30 years? I think the standard deviation is 30 minutes too. But there's a large variation in how long we spend in the shower, but it turns out that on average, 2 minutes out of every 8-minute shower is waiting for the hot water to arrive. That means we're actually only taking 6-minute showers. Now, I don't care if you take an 8-minute shower or a 6-minute shower. I want you to be in the water taking the shower, not waiting for the hot water to show up at the shower head. Okay? And so I'm trying to fix that with all the design work we're doing and the analysis we've done. And you can see the water savings are pretty good. But again, most of these savings you see here are related to the use by switching from normal flows to low flows. So let's look at another way of looking at these numbers. You'll notice that the graphs all go from 0 to 50, and there's a minus. Sometimes we actually saved energy, not very often. And so how much energy was wasted is in black, the loads not met are in gray, and you can see it varies from, this has very little energy waste with the water heater in the laundry and a central manifold in the laundry room. That's pretty good. It's in the compact plan. We have the wet rooms and the water heater close to each other. Okay? It was intentional. It's part of the design phase. Water heater in the laundry is always a good choice, except one zone without recirc, okay? Because you've got longer pipe. It's designed to have a recirc loop. Why? So that every faucet and every shower has the same length of pipe from the loop to the fixture. Everyone gets the same service. In all other cases, they don't get the same service. So it shows less energy, but it's not equal service. I'm sorry, it's still not right. It has to be equal service, then how much energy. So now this is looking at compact design, smaller pipe and lower flows. I recognize it's a little busy. We use 3/8 inch pipe in some cases, no 1-inch pipe. Sometimes we use 3/8 and no 1-inch pipe. And now you see some negative numbers. 1, 2, 3, 4, 5, 6, 7, and one more that's not on here, which is for regular flows with 2 water heaters showed a negative consumption in energy wasted. It went negative compared to the base case. That's pretty impressive. That's all the best cases I just showed you on the other page. But look at this. Even with that, the service levels, loads not met, are almost always above 10, 15%. Remember, we started at 21%. So they're better, but they're not a lot better in service, because the way it got analyzed was assuming whatever the service is, it is. And then you compare the energy. So be better if we tried to figure it out differently. We just didn't have the ability to do at the time to do it. So now I want to give you some hope. The best one-story floor plan I've seen so far is based on a short story. I was at a conference that I help sponsor out here in California, the Dry Climate Forum. Some of you have heard of it. Some of you probably been to it. And it's for people who live in climates without, humidity, like California, sort of. Anyway, but we talked about water, and the fellow who's the Stockton Habitat for Humanity builder came to the conference several years ago now, and he says, we chatted after dinner. He says, this is the floor plan I got now. What should I do? And we talked for about an hour, and he went off, and I didn't hear him again for a while. And a year later, I see him at the same conference, and he comes back and tells me, this is my new floor plan. I'm down at 15% if you count the whole wet room. But you're not supposed to count the whole wet room. You're only supposed to count where the plumbing goes, because it's where the valves are, not where the end of the tub is. Okay? And they're basically a U going from here around to here. And it's 4% of the floor area. That was his first attempt. So we chat about it. We talk about it a while. He goes away for another year and comes back with this design. We're down to 2.5%. The water heater is now tankless. It's over here on the wall in the corridor. Washing machine is right behind it, and the plumbing runs down the spine of the building to the kitchen sink on the opposite end. And that's version 2. We're at 2.5%. Version 3. He managed in this case to put a tankless water heater over one of the toilets, the home run manifold over the other toilets, and he went left and right to get to all the fixtures. he has less than 10 feet of twigs to every fixture. He has one very tiny plumbing wall. Now, I'd say he gets a gold star for being anything below 20%, 25%, and he is down in the 1% range. I'm not quite clear how we're going to do heat pump water heaters yet, although I have seen a version of a heat pump water heater that can hang on the wall above the toilet. And I think that would be a perfect application to keep the same strategy, and he'd still be at 1%. I'd say that's very good. Okay. The best two stories so far, many of you know the person who designed this, but all of us in the US own this building. This is in Gaithersburg, Maryland, at the NIST facility, National Institute of Standards and Technology. They have a net zero home they've been analyzing for a while. And this is the floor plan. Water heater is actually in the basement, and all of the wet rooms are in this quadrant of the building. And we know the architect, right, from summer camp. And I asked her, how did she decide to do this? And she said, well, I met this guy named Gary about a decade ago. He explained this to me. It made perfect sense. But I never talked to him about it. I didn't know what the design was until after the building had long been built. It makes sense to do it. This is a nice house. It happens to have all the wet rooms close to each other and right above the wall. And that's it. Time for questions.
Time for applause. Gary, fantastic. Great job. And
thank you.
Amazing timing. That's a lot of information in a very short amount of time.
Did I do it? We get done in about the time we discussed?
You're perfect, because we even used up a little bit of time with Dylan getting acquainted with Discord. So well done. And you do have a lot of questions. And
right. So let's just go to the top and work our way down.
Yeah, I'm going to throw the first three in the queue. The third is a comment. So if Graham, if you don't want to comment, let me know in the chat and I'll move on after that. But Sarah Waring, if you would like to unmute and ask your question, please go right ahead. Sarah, are you with us? You look unmuted. You look like you're here. So Sarah asked, where's her first question? Because she had two. Okay, is it more efficient to use electric resistant point of use water heating than a heat pump with a longer pipe run?
Great question.
Right?
Yeah, so I'm not sure it's quite the right question. And so the question is, do the two choices give the same level of service? So if the heat pump is in the garage, which it often would be here in California, or in the far corner of a basement and houses with basements, then yes, it may be more energy efficient to have the one heat pump water heater, right, rather than a resistance element under the kitchen sink. But you're not providing hot water very quick unless you do something else that takes more energy, right? So if you're willing to, if you think it's okay to put up with waiting for a minute to 2 minutes to get hot water at your kitchen sink every time you want hot water at the kitchen sink, because you're willing to pay for that inefficiency of water and time with a more efficient heat pump, go for it. That's what we're all doing. I don't think it's the right answer. I think what we should be designing for is to give equal levels of service and figure out how to do that most efficiently. If the kitchen sink is within, I don't know, call it a quart in plumbing terms of the water heater, I would just use the one water heater. I'd give up on perfection at that level. But if it's, across the far side of the house, like is often the case, right? I think architects on the call, I think you lose your license if you put the water heater close to the kitchen sink and to the bathrooms in the same building. Why do I think that? Because we don't do it. We keep putting them all over the place. I'm picking on you, but I'm your friend here. I want to help you figure out how to fix it.
Oh, that's okay. It's the architects who aren't on this call who aren't learning these lessons. So the ones here are your friends. they're on your team. They want efficiency and equal service, right?
Right. So Shannon, to finish the question for Sarah, if the distance to the water heater and the kitchen sink is close, and close is a volume term, and I'm going to pick a quart as an obvious number for a minute, then I'd be willing to put up with some lack of perfect service in order to have the more efficient heater. But if it's on island sink anywhere on the house, but usually they're way away from the water heaters, an island sink slab on grade, I would put a resistance water heater in that cabinet every day of the week. It's really hard to plumb it well unless you've got very special abilities in the design of the house. I would give up on the perfection of energy to have the localized water heater to improve the service, because literally I could have hot water within a few seconds by doing that.
Yeah.
Now I have to pay for the extra water heater, and I've got to pay for the wiring to make it happen. You've got to think about it a bit.
And what about the labor piece?
It's probably much less labor than running the second pipe, because the water heater is not a whole lot bigger than our first computers were, right? And so it's, I think it's plausible. It's an interesting problem and an interesting question, but I think that the correct answer is to have architects give us better floor plans. Let's just solve this problem the other way, because you're asking me to put Band-Aids on a problem that I shouldn't have had in the first place.
Fair enough. Well, I think that
next
answered
question.
Sarah's question.
Thanks, Gary.
You're welcome, Sarah.
Reed Rollins, would you like to unmute and ask your question?
Good, you hear me?
Yeah, I saw your question too. It's great.
So I got lucky in a building we designed and built. We have a recirc line that ended up being, we yanked the pump out because we didn't need it. So how do you design, or what is the physics, or what's it take to design a gravity-fed recirc line?
Slope.
Well, yes.
But you have to have it consistently up to a high point and consistently down back to the water heater. Otherwise it won't do it.
So even up, even down.
Yes, it doesn't have to be even. It has to always slope up and always slope down. It doesn't like to have bumps to go up and down. It doesn't like to do that. Okay.
Yeah.
So it doesn't have to have much slope. But you're actually not, I'm not sure you're asking quite the right question. Why do you like your gravity loop?
Because I don't have to feed a pump electric.
Great. How much energy is the loop costing you in hot water, in heated water?
Yes. If you have a very large building, you kind of, I'm assuming that recirc lines are the preferred way.
Well, you have a recirc line. It just doesn't have a pump.
Correct.
So we analyze for that. If you go to my company website, you can find a link to some early papers I wrote analyzing circulation loops. I'm pretty sure we'll cover that again at some point in this webinar series, but I wrote about this some years ago, and the basic math is as follows. If you have, so let's assume you have a recirc loop and it has a pump, which you had before, okay? You just took it off. So let's assume you were running the loop at a gallon a minute, and you were running it it was about a 5-degree temperature drop around the loop. Okay.
Yeah.
And Reed, those are plausible numbers. I've looked at lots of systems and it's in the ballpark. It might be a half a gallon and 10, I don't know. It's in that ballpark. And let's imagine your household uses about, I'm going to use gas for the moment. Someone's got their mics on with background noise.
Yeah, Sean, I think that's you. I'm trying to mute you, but it's not working.
So thank you. So back to Reed's question. So let's imagine you had that, and let's imagine your household is sort of 3 people and you're using $150 worth of hot water a year. And these are plausible numbers, okay? The recirc loop is costing you $300 a year to keep the loop warm, and your use is only 150 bucks. Energy goes to the loop with the pump at a gallon a minute and 5 degrees delta T, 24 hours a day. I'm just picking the dumbest way to do it, okay? And so if you take the pump off, the water slows down in speed. Is that correct?
I don't
Probably.
know. Okay.
Probably.
I would guess yes.
Okay. So no one actually knows the answer because everyone thinks it's too low to measure. And it's really hard to measure because the flow rate is really low. But you can infer what's happening by measuring the temperature difference between the water leaving the water heater and the water coming back, because it leaves at 120, 30, 40 degrees and it comes back at some lower temperature, right? And it won't come back 5 degrees lower. It'll come back much, much colder. It has to. That's how a gravity loop works. It has to have a delta T for it to drive the water around the process. Okay. And when I finally got a chance to measure this, there's a fellow I know who helps run the Plumbing Union Training Center in San Jose. He says, I have a gravity loop. And I said, when I come back next time, can I come measure it? And I did. And we found that it was moving, the water temperature was dropping 50 degrees around the loop. Not 5, 50. So from that, I inferred that the flow rate's on the order of 1/10 of a gallon a minute, which is about what I'd expect it to be in the ballpark. So it turns out everything is roughly proportional to flow rate and delta T. And I don't care if you have a pump doing it or a gravity loop doing it, but you always have this proportionality. If you slow things down, you're going to have bigger temperature drop. If you speed things up, you'll have less temperature drop. And whenever I've analyzed it, I keep finding it's on the order for a 27 loop. It's very close to what you'd see for 5 degrees and 1 gallon a minute, and do the math. And it ends up being about 300 therms a year. So a gravity loop with a pump or without a pump, I think is on the order of 300 therms a year of energy. Now, if there's 20 of you in the building using hot water, 300 therms ain't so bad. If there's only one of you, it's a big deal. So I think that what we have to ask, Reed, is how could we design a better loop? You want a loop. Why do you want a loop? Hot water shows up quick, right? That's the service level you want. Now let's figure out how to reduce the energy impact of your loop.
So do you always design without loops as best you can? If you can,
no, I actually don't. I design with loops because architects give me bad spaces.
Right.
They're great. Sorry, let me change that. Architects give me hard to build with for infrastructure spaces. I like a lot of the buildings I see. I'm not pointing fingers at that. It's a question of the layout. So unless I'm getting a building with a very compact floor plan,
right,
like you saw for the best case, I would be putting in a recirc loop. Why? Because the loop lets me decide how long the twigs are, and the length and diameter of the twigs tells me time to tap, and then I can get a consistent time to tap. I can predict and provide a consistent level of service. So the real question you're asking me is, how do I design a loop that's energy efficient? Fair enough?
Yeah. So should you design one with a pump or try to do gravity?
With a pump, because you don't actually need the hot water to flow all the time. So a couple more questions for you to sort it out. Do you plan to sleep tonight? Say
Hopefully.
Yes.
Hopefully.
Right? Hopefully, right. Do you plan to use hot water while you're sleeping?
I know where you're going. You're right. Yeah.
Okay, so we're going to stipulate that that's 8 hours a day, roughly speaking. Okay, maybe you don't sleep so well anymore like me and it's only 6 hours a day, but whatever it is, it is. And then someday in the future, you actually plan to go back to work and you won't be home for another 8 hours or so a day. So that's 16 hours out of the day. And I work from home, and I will tell you that I do not use hot water every minute of the time I'm working. Remember, it's spaced apart in time and it's very tiny volumes. Except for showers and washing dishes and sometimes washing clothes, the volumes are trivial for hot water.
I agree.
So,
I think where you're going, and it sounds like I should go find a nice energy efficient pump and stick it back in there.
well, actually, I want you to go look up a specific type of control for the pump. It's not about how efficient the pump motor is. It's about how efficiently you tell it to turn on and off.
Oh, no. Yeah, absolutely. Don't turn it on at all at night. Just come on peak times.
Well, it turns out that even that's too much. You can do better.
Really?
And so, yes, the best design of pump is a control strategy that is demand activated. And I will talk about that in future webinars about specifics and why and all that stuff. I actually did another research project looking at recirc pump controls on my own home because I have a house that came with a recirc loop so I could analyze for this. And you can see what the numbers are, but the far and away the best. So what do? We looked for a set of controls, Reed. 24/7 is a bad choice. Timers for a couple of hours in the morning, a couple of hours at lunch, and a couple of hours, 3 or 4 hours in the evening are sort of another typical choice. But then timers go out of whack because, you know, we have power failures for minutes here and minutes there, and that just drives the timer nuts. Anyway, I tried intermittent timers. I tried aquastats. which are basically a temperature controlled timing cycle. It's very interesting. It's better than I thought it was. And I tried demand activated. And I've got a presentation I've done before and will do again on this sort of stuff. I was looking for any way to reduce the loop losses by at least 80% and the pump runtime by at least 80%. Those sound like pretty good goals, right?
Can I ask you to hold that thought for just
I can.
a minute? Thank you. And you've generated a lot of action in the chat on this subject, so we may end up going out of order when we come back. But it's time to close out the first hour and go over to Zach. So everybody hang in there and we'll see you on the other side.
Great, thank you. Thanks, Gary. This is really fantastic as we expected. And thanks everybody for being here. Everything that we do at the Accelerator comes thanks to support from these fine organizations, our sponsors. So our founding sponsors are 475 High Performance Building Supply, Baxt Ingwe Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Rockwool North America, Stocorp, and Zola Windows. Our champion sponsor is SIGA, and our stakeholder partner is NYSERDA, the New York State Energy Research and Development Authority. Our patron sponsors are AeroBarrier, BR+A Consulting Engineers, Brennan Air Tightness and Insulation, Innotech Windows and Doors, Sanderson Sustainable Design, and US Engineered Wood T-Stud. So for announcements, tomorrow we have a very exciting and unique happy hour. We're going to be joined by a group of students who are going to be presenting their solar decathlon entries, a bunch of winning entries from the University of Arizona. So please join us for happy hour tomorrow. Tonight is the last construction tech for a few weeks, and tomorrow is the last happy hour for a few weeks because both shows are taking a break in August. So I want to encourage everybody to check out the podcast. And we have none other than our very own Mark Willey from T-Stud and co-host of this show on the Passive House podcast right now. It's a great conversation between Mark and Matthew Cutler-Welsh, the co-host of the podcast. So check that out. We also have a bunch of Passive House podcast bonus episodes that were recorded at the North American Passive House Network Conference in June last month. And those include short interviews with Shannon Pendleton, also co-host, as we all know, and Kevin Brennan. So we got lots of construction tech interviews. And if you haven't gotten enough of co-host interviews and you haven't taken in episode 45, you can hear Sean St. Amour's story and his interview with Matthew Cutler-Welsh as well. So we're really excited about the programming that we're putting together for you in the fall, and we'll be making announcements throughout August about what's coming up on the show. And in the meantime, there's lots to listen to on the podcast. We've actually had 10,000 downloads in the last month of the podcast, so it's really taken off. So with that, thanks everybody.